This is problem number 4 for problem set number 1. A copper calorimeter can with mass 0.1 kilogram contains 0.16 kilogram of water and 0.018 kilogram of ice in thermal equilibrium at atmospheric pressure. If 0.75 kilogram of lead at 255 degrees Celsius is dropped in the calorimeter can, what is the final temperature? Assume no heat is lost to the surroundings. Okay, so we are given the mass of copper, 0.1 kilograms. The mass of water is 0.16 kilogram. The mass of ice is 0.018 kilogram. And it mentions that they are initially in thermal equilibrium at atmospheric pressure. So what that means is that all these guys have the same temperature initially at same temperature. Okay, and if we look at this graph right here for water, where can water, liquid water, and ice coexist at the same temperature, according to this graph? So ice is a solid, water is a liquid. Where could they coexist? They coexist right here at the melting point, which is 0 degrees Celsius. So I know that the initial temperature for copper, water, and ice is 0 degrees Celsius. Okay, what else am I told? I'm told the mass of lead, as given, is 0.75 kilograms. Okay, the initial temperature of lead initial is equal to 255 degrees Celsius. And I am to find out the final temperature, meaning once copper, water, ice, and lead have reached thermal equilibrium, and they're all the same temperature, what is TF? Okay. So, sounds like a calorimetry problem, right? Since calorimetry means heat transfer between two or more systems in thermal contact. So all the copper, the water, ice, and lead, they're all in thermal contact right now. So this is a calorimetry problem. And I know that in calorimetry, the sum of all heat transfer equals 0. Right? And that becomes at mass times specific heat times temperature change. So T naught for material I. And then plus or minus, when there's a phase change, the mass times the latent heat of fusion or vaporization, depending on the type of phase change, and that equals 0, right? So this part of the equation is the heat transfer necessary to change temperature within the same phase. So this is for the heat transfer to change temperature within the same phase. Okay, and this one is for the heat transfer necessary to change phase. Heat transfer necessary to change phase. Okay, so to change phase, we use that. And for the same phase, we use this guy. Okay. So how do I know which materials are gonna be in the same phase or change phase, right? I would have to look at the melting point and boiling point for copper, for water, and for lead. So I went ahead and did that. I just looked on Google and I've got it right here. This is all from Google, these guys in green. Okay, so let's stick that up here. Okay, so I know that my initial temperature is 0 degrees Celsius. The lead that I introduced to the system is initially at 255 degrees Celsius. So I'm just going to look at the melting point and boiling point of each of my materials and see if it's within that range, within that temperature range. So for copper, the melting point is 1,805 degrees Celsius, and the boiling point is 2,595 degrees Celsius, well above 0 degrees or 255. So I know this will not change phase. Copper will not change phase. Okay. For ice, or for water, the melting point is 0 degrees Celsius, and the boiling point is 100 degrees Celsius. So I'm going to assume my ice is going to melt because we introduced something, we introduced the lead at 255 degrees Celsius and initially our system was at 0 degrees Celsius. So I'm going to assume ice will need this equation for heat transfer necessary to change phase. And for lead, the melting point for lead is 327.5 degrees Celsius and boiling point is 1,740 degrees Celsius. Okay, above our initial temperature and the initial temperature of lead that was added to the system. So I know lead will not have a phase change. Okay, so now I can go ahead and use this equation. I'm going to use a thinner pencil. Hopefully this can still be read. Okay. So I have the mass of my copper times the specific heat of my copper times the change in temperature of copper. So Tf minus T naught. Okay, and then what else do I have? I also have water. So I have the mass of my water times the specific heat of my water times the final temperature minus initial temperature for water. Okay, plus the mass of my ice times specific heat of ice, which is the same as specific heat of water, times the change in temperature for ice, right? But also, remember, ice is going to experience a change of phase, so I also need to use this equation right here. So plus the mass of ice times, would I use the latent heat of fusion or vaporization for ice? Well, ice is a solid. I assume it's going to melt to liquid, so I would use latent heat of fusion, right? Because for latent heat of fusion, that's between liquid and solid and vice versa, and vaporization is between gas and liquid and vice versa. So I will use times the latent heat of fusion of water plus the mass of lead times the specific heat of lead times a change in temperature of lead. So the T final, since they all reach thermal equilibrium. But remember, lead was added at a later time, and the initial temperature of lead was 255 degrees Celsius. So minus temperature of lead initially. Okay, and that's all going to equal 0. Okay, and just to clarify, this is for the heat transfer necessary to change the temperature for copper, since it's just within the same phase. So copper This is same phase. It's still going to be a solid. For water, it's still going to be a liquid, so this is for water. Same phase. This is for ice, the heat transfer necessary to change temperature for ice. So this is for ice, same phase. But also, we assume that ice will melt, so we also have ice change phase. And this is for lead. Lead. Still a solid, so same phase. Okay. So far, what color should I use? I guess I'll use blue. So far, I know the mass of copper, TF. I know the final, or no, we're looking for TF, right? So we want to know TF. We know T naught. We know the mass of water. We want to know TF. We know T naught. We know the mass of ice. We want to know TF. We know T naught. We've got the mass of ice. We know the mass of lead. We want to know TF, and we know the initial temperature of lead. So we need to find out the specific heat for copper, water, lead, as well as the latent heat of fusion for water, right? And I found that through Google again. So these you'll just find on Google, or maybe for a test, it might just be given to you guys, or you guys might be given a chart to find this. Okay, so I'll put this right here. Make it smaller. There. Okay, so on Google, I was able to find my specific heat for copper, specific heat for water, latent heat of fusion for water, and specific heat for lead. So it looks like now all I'm missing is what I'm trying to find, which is the final temperature. Okay, so I will try to use algebra. Oh, one more thing. I know that the initial temperature of the system was at 0 degrees Celsius, right? So I could cancel that out. So what color should I use? I'll use purple. I know that's 0, that's 0, that's 0. Yeah, okay. So now I've got the mass of copper times specific heat of copper times the final temperature plus mass of water times specific heat of water times the final temperature plus mass of ice times specific heat of water times the final temperature plus mass of ice times latent heat of fusion for water plus the mass of lead times specific heat of lead times the final temperature minus mass of lead times specific heat of lead times the initial temperature of lead is equal to 0. Okay. So that becomes, so I could move this and this to the other side of the equation, right? So I would have mass of lead, specific heat of lead, times the initial temperature of lead, minus mass of ice, times the latent heat of fusion for water, is equal to the final temperature times mass of copper times specific heat of copper plus mass of water times specific heat of water plus mass of ice times specific heat of water, okay, plus mass of lead times specific heat of lead, okay? So that becomes, so then the final temperature is equal to mass of lead, mass of lead, specific heat of lead, initial temperature of lead, minus mass of ice, latent heat of fusion for water, all divided by mass of copper, specific heat of copper, plus mass of water, specific heat of water, mass of ice, specific heat of water, plus mass of lead, and specific heat of lead, okay? So I know all of the values for everything in here, right? I know the values for everything in here. So I could find my final temperature. Pretty much if you get to this point and you got that right, I think you'll probably end up with 90% or 99% of the points. You basically know what you're doing at that point. And yeah. So I'm just gonna plug in the values. So we have mass of lead is 0.75 kilograms. Specific heat of lead is 130 degrees or 130 joules per kilogram times Kelvin. And the initial temperature of lead is 255 degrees Celsius. Okay, minus the mass of ice, which is 0.018 kilograms. And the latent heat of fusion for water, which is 3.34 times 10 to the 5 joules per kilogram, divided by mass of copper, that's 0.1 kilograms. Specific heat of copper is 390 joules per kilogram times Kelvin, plus mass of water, that was 0.16 kilograms. The specific heat of water, 4.19 times 10 to the 3 joules per kilogram times Kelvin. Mass of ice, that is 0.018 kilograms. The specific heat of water again is 4.19 times 10 to the 3rd joules per kilogram Kelvin. Okay, plus mass of lead, that's 0.75 kilogram. And specific heat of lead is 130 joules per kilogram Kelvin. Okay, and if you plug that in your calculator, you will get that the final temperature, which is what they were asking for, right? What's the final temperature? The final temperature, if you plug all this in the calculator, is equal to 21.36 degrees Celsius. There you go.